Hey there, awesome physics students. I wanted to go through some of the examples with forces in the body and to help you understand why these forces are generally so large and what are the alternatives that evolution could have picked for us. So the first example I want to talk about is again this forearm situation. So here's your forearm. This is your lower arm. That's a free body diagram for that. And we have the biceps muscle exerting a force up on the forearm. That's FB. And then it's attached to the upper arm here, and there's a joint between the upper arm and the lower arm, and that joint force is going to be down on your forearm. There's also the downward force because of the weight of your forearm. And then if you're holding something in your hand, then there's going to be the downward force of that load. If you're, typically we want to do useful things, pick up things with our hand. So why is this biceps force so large? Well, if you look at the distance between let's put the axis of rotation at the joint here, the distance between the load and the axis of rotation is huge. And so even a very small force here is going to produce a very large torque. And so to counteract that torque, your biceps force must pull up. But the problem there is that the biceps force is exerted a very small distance from the axis of rotation. So why did nature do this? It seems like a stupid idea to put the biceps so close when if you had the biceps farther out, that biceps force wouldn't have to be so big. So generally the distances here, this is about 30 centimeters roughly, and maybe this is like 3 centimeters. So roughly the load is about 10 times farther from the axis. So that means the biceps force is generally going to have to be 10 times bigger to produce this a counter torque. If you put the biceps force out here, think about what that would mean from a physical standpoint. That would mean that your biceps, instead of attaching down here, would attach here near where your wrist is. Well, you can kind of imagine that, when you look at your biceps shrinking in length when you contract the muscle, it doesn't actually move that much. It only contracts maybe a few centimeters. And so if the biceps were attached here at your wrist, you would be able to move your arm from here to here, maybe just a few centimeters. Your range of motion would be incredibly tiny and terrible. Yes, you would be able to lift massive objects, but you wouldn't be able to, take your arm and extend it out like this. Look at this incredible range of motion we can have, and that only, our biceps, to produce that range of motion, only has to contract a few centimeters, maybe 5 centimeters or so, to produce this incredibly huge range of motion. And the trade-off is that we can't hold as large of loads. But for some reason, evolution decided that was not as important. Let's look at another situation with the triceps. So here this is again the forearm, and we're holding it out like this, and we're pushing on the wall that way. And so up here we're touching the wall, and the wall is pushing back on our forearm, our fist up here at the top. And I'm going to put the joint right here. The triceps actually attach on the bottom here of the arm. And so the joint is right here, and then the triceps are going to be attached here. Because the triceps can only shrink in length, then they can only pull, and so they're going to pull this way. So this is going to be the force from the triceps. This is going to be the force from the wall. And there's a joint force here. Of course, there's the weight down of the forearm, but that's not going to come into play in this particular example. So which way do you think this joint force must point? Well, based on the two of these, the joint force must point that way in order to produce zero horizontal acceleration. This scheme also matches well with some of the other schemes we've seen for stability. So this will produce the sum of the torques will be 0 here. But again, the wall to joint distance is huge compared to the wall to triceps distance. And so the triceps, to produce a counter torque to oppose this wall torque, the triceps force is going to be enormous. And again, it's just the range of motion situation, right? If your triceps were instead to, let's say you extended your arm back this way and your triceps attached here, that would mean that you would have this weird like teeter-totter arm shape. And yes, you could produce enormous forces, but your triceps are only going to be able to shrink or change in length by a few centimeters, and so you're going to be able to move much smaller distance. In other words, your range of motion is going to be sharply affected. Let's do one more situation. Here's the deltoid. So here, this is the deltoid muscle up here, and it's attaching like this at some angle to the arm, and it's pulling upward on the arm like this at some oblique angle there. And you're holding a bag here, so there's a force, there's a load force here. And there's also the weight of your arm down, and then there's going to be a deltoid muscle, which is, here's your joint. There's going to be a deltoid muscle here that's pulling up at an angle like this, and then there's going to be a joint force here. Now, which way do you think this joint force points? Well, these two forces point down. This one points up generally, so I guess that because this distance is very small compared to these, this deltoid force is going to be, again, really large. And so I'm going to need another large force downward to offset this one. So this joint force is going to be roughly, not exactly, but roughly opposite of the deltoid force in order to sum the torques to 0 and sum the forces to 0. So this is the force from the deltoid, and this is the force from the joint. All right, so if this is the situation here, again, why does the deltoid force need to be so big? Well, it's because of the distance, but actually in this case, it's not just the distance. The angle is at this weird angle. It's only the part of the force that's perpendicular to the r vector, and the r vector is pointing horizontal like that. It's only the perpendicular part of this force, this part of the force, that actually contributes to the torque. And because this angle is so sharp, and I've drawn it actually bigger than it would be, that means that the deltoid force has to be even bigger than if the deltoid, imagine if the deltoid just pulled straight up. Now this deltoid force has to overcome two effects, the small distance and this tiny angle. And so the deltoid force is going to be enormous. And so your joint force correspondingly has to be enormous to cause the sum of the forces to be 0 here. And again, the reason for this, that evolution chose this for us, is that your range of motion needs to be large because you want to be able to move your arm all the way up to all the way down. And yeah, that's the trade-off there. All right. Hopefully this helps you give you some overview of why our body has these trade-offs in our body and how this connects with biomechanics and torque.